structure. And then the disturbance. The noise is the measurement, and then this is the output, Y. And we found out that Y is equal to T YR minus T plus the disturbance. Let's send that. And this T is S. And the S is the sensitivity. And the T is the co-sensitivity. And then from these two equations, it says that S plus T is equal to unity. And we put conditions to reject the disturbance. S has to be small. And once we have this, then this means from here that T is large. And T is large means that the suppression of the noise is not very good. So we have the other requirement is the noise suppression. And this requires that T should be small. And so we said that these two are conflicting requirements. Okay, then now we took this and we looked at system uncertainty. We looked at one configuration, which is the multiplicative uncertainty. Then the system is stable if del m is less than 1 over absolute value of t, or if absolute value of t is less than 1 over del m. And we said that this distinction gives us two options. Again, remember the t is gk, I plus gk. I want to select the control gain to satisfy certain uncertainty or certain bounds on the uncertainty of the model. So if this is known, then I want to select the gain such that the t is less than this bound. So if you look by looking at this equation, I want to select the gain to be smaller than certain number, and that's where the name came from. Small gain theory. I want to reduce the gain as much as I can to accommodate this parameter uncertainty of the model. This is one way of describing it. The second, for a given gain and a given system, if everything is known here, then this is the upper bound of the uncertainty, beyond which the system go to become unstable. So on the right-hand side of the inequality, this is all known. And here we set limits on the parameter uncertainty or the controller gain. So here is the bounds or the limits on parameter uncertainty or control gain. And from all this, we see that the uncertainty acts as if we have an external disturbance acting on the structure. Exactly, this acts as the disturbance W. Now, the example that I gave you, we'll go over it again. Example, we had a rod like this or like this. This is 1 meter long. So I either divide the rod to 2 elements or 1 element. And this would be a higher order system compared to this. Or this is more accurate than this. So now for the system that we have, we either have 2 elements or 1 element. For the 2 elements, we have to have matrices 2 by 2, the stiffness and mass matrix. I'll form the A matrix, the B matrix, and the C matrix. The same for the 1 element rod. I'll form the corresponding matrices. And then now, I'm going to plot the body diagram for the 2 cases. And also, I'll plot the root loci for the 2 cases. So we have the A, B, C, D matrices. I can generate the numerator and the denominator, take them, put them in body diagram for any frequency range, generate the magnitude and phase angle. Okay, and then the root locus, I need only the numerator and the denominator for either one of the two cases. And then I plot these. This for a minute. The important thing is this diagram. For the fine mesh structure, I have this characteristic. I have 2 by 2 matrices, so it becomes the A matrix 4 by 4, so I have 4 roots. I have 2 and 2. Then now the root locus will be generated from these two poles, and these two poles looking for the zeros. There is no zeros, so it will go to infinity. So from this point, I can increase the gain slightly until I hit this line. Then the roots become positive and the system become unstable. Okay? So now, for the high order system, I can see this instability. If I make the system very, very small, everything will look to me stable. And this gives you wrong impression about the system. You can simplify, but don't oversimplify, because you lose the physics of the problem. So now, in the low order, I start from these two poles, and I go to infinity. Any value of the gain make the system stable. Here, any small change of the gain will make the system unstable. What is the difference between these two? Is this uncertainty. If I'm not sure how the model fits the actual system, then I have some doubt. The doubt, I can express it by the difference between this system and this system. Okay? Of course, if these doubts, you require them very accurately, then this defeats the purpose. Because I want to make it simple, but at the same time, I want to avoid modeling this accurate case. So I'm going to say, instead of looking at the actual difference, I'm going to put a cap on my uncertainty of the system, as you will see now in a minute. So now, this is very simple, but it's not accurate. This is accurate, but it requires a lot of computation. The difference between these two define this uncertainty. Now, how would I get this uncertainty? This is the root locus. The uncertainty comes from the magnitude and the magnitude of the transfer function. The difference between these two, normalized with respect to the nominal plant, will give me the amount of uncertainty. So now, you have this graph. The higher order system has more resonances. The lower order has less resonance. Shift on the positive or the negative side is an error. That's why we look at the absolute value of the uncertainty. The absolute value of the uncertainty. Now if you look at this graph, the uncertainty goes high and low and so on. I don't care about all this. I'm going to say now the uncertainty is below this line. I have one line. I'll say, for example, this is 10. The uncertainty is 5, for example. So I have anything below 5 is uncertain to me. So I'll just put here a maximum bound on the uncertainty level. Now this maximum bound on the uncertainty level has to be lower than this to be stable system. So if I know this exactly, then that's fantastic, but defeating the purpose. I will say I know the system within 5, 10, 15, 20% error. Okay? And the higher you make this, the performance has to be lower, because you cannot have very high doubts and get excellent performance. So if you know the system exactly, then you'll get the best performance. The more you put doubt on your knowledge about the system dynamics, the performance will degrade. So now this is my uncertainty. Now I'm going to put here the effect of the controller. Okay, the effect of the uncontroller is right here. This command is a new command now that we did not do before. I have the open loop system. I have the G of the system. I have N and D. Now I want to get, for this system, I want to close the loop. I want to close the loop. So now I have something like this. Okay, I'm going to have here a gain K, and then I'm going to close the loop with negative feedback. Negative feedback. So this G, I know numerator and denominator. So I come here and I say the numerator and the denominator times the gain. The gain that I selected for this problem is one number. It's constant value. It is not a transfer function. If it is a transfer function, then I have numerator and the denominator. But I selected only a constant value times the numerator. I want to close the loop now. And I will close it with negative feedback. So I put here -1. This is negative feedback. And then put this command, close the loop. So from the numerator and the denominator of the open loop, form the numerator and the denominator of the closed loop. Now I have these, then I can plot the response. Again, using the both diagram, and I can plot the response of the closed loop. Response of the closed loop. Why? Because this T is GK. GK. The open loop is only GK. G and K. Now when you close the loop, negative feedback, the result is this T. This T. Now I'm going to plot the body diagram for the closed loop as function of the frequency. Okay? So now the result is this graph that you have. Okay? And the graph that I have here is for gain of 0.1. Gain of 0.1. Now they're barely touching. They're barely touching. The 1 over T, I'm sorry, these two, they should be flipped over. The uncertainty is the red. And the 1 over T is the blue. Okay. Now let's look at, you can plot many of these and plot them on top of each other. I did this plot which you don't have. This is the uncertainty. And then the blue is the low gain, which is the 0.1. They're just barely touching. Now if I increase the gain to 1, the 1 over T is no longer greater than the uncertainty. So this inequality is violated. This inequality is violated. So now this is an unstable system. For higher gain, we become unstable, so we have to have small gain to have system stability. And this is very obvious. In any control system, if you drive something very fast, you can damage it before you can control it. So you have to drive it as slow as possible, and at the same time accommodate your lack of knowledge about the system dynamics. Okay? So this is very clear now. Now I'll leave this section for maybe this lecture and next lecture, and then we'll get back to it. Okay? So again, the summary of all this, we'd like to select the control gain to number A, reject external disturbances. And the profile of these external disturbances, I can define them with some weighting function. Okay, number B, of course at the same time, suppress any measurement noise. There's no distinction between these, except in the S and the T. And then the last thing, number C, is to accommodate parameter uncertainty. Okay, so this is the main topics, and we covered following preliminaries. Number A, the sensitivity and co-sensitivity. And then number B, we can shape these two parameters, S and T, using weighting matrices, weighting transfer functions. WS and WT. And these, if you remember, they were like this. And we found out that Z1 is equal to minus WT times T times V. And Z2 is equal to WS S times W. And from here we said, I am going to monitor these two parameters. Why? Because these two parameters come from the measurement noise and external disturbance. I want the transfer function between what happens because of the external disturbance as small as possible. So I want to make the norm of this, the absolute value of this, very small, the absolute value of this, very small. So now we can shape the required S and T by proper weighting matrices. And we will show some examples how to do it. So now from here, we said I have to have the T is bounded by WT inverse, and the S is bounded by WS inverse. Okay. The third thing that I did, which was the small gain theorem, and we summarize it in one of two ways: either the absolute value of T is less than 1 over delta M, or the absolute value of delta M is less than 1 over. Now all this is preliminaries to the H infinity. I'm going to do one more thing, and then we'll go into H infinity. You cannot do any of what we've covered by the classical methods that we talked about in the beginning. I cannot shape this or this or this as I like, or I cannot accommodate all these in the design of the controller. Okay, now we will solve this problem using the Hamiltonian matrices. And I'll begin first, number A, for the LQR. We have the performance index. Again, was J is equal to 1/2 integral from 0 to some final time x transpose qx u transpose ru dt. I solved this problem with one way that you have in the notes by making assumption on the system stability, and we showed that this J let's see here now, find the control gain to minimize J, and we showed that I can write J and find this. This is our objective. We solve by J was equal to 1/2 x0 transpose P and x0, and we said that minimum J requires that del J is equal to 0 or del P is equal to 0. going to start from here. And the conditions for optimization of this will yield to the Hamiltonian matrix that we covered. If now instead of this, I say my J is the infinity norm between this and this, or the infinity norm between this and this, or I can combine it, because I can make this a vector, and I can make all the noise, the disturbance, the uncertainty, I can make them all one vector. And then now minimize the maximum infinity norm between this and this. So now I can redo it in another form. The result will be another Hamiltonian matrix. The solution, straightforward, we can extract the Riccati equation, and then we can solve for the control again. So this is unifying type approach for this problem. Okay, so now from here, I have to add one more line. And we'll say now, find the control gain to minimize this, and I have to satisfy the equation of motion of the system. That's BU. Now let's say here use Lagrange multiplier method. Then my J is no longer this J, and I have to augment it, and I call it JA, and 1/2, and then I'll have here X. And I put 1/2 here, and I have to augment to is the equation of motion, and I'll augment it by twice lambda. And I'm going to make it lambda transpose, so the units will match. And then here, AX BU minus X dot and this is the delta T. So now this is the main objective function of performance index. When I use the Lagrange multiplier lambda, I augment the performance index with how much I violate the constraint. So this is the effect of the constraint. If I am satisfying the constraint, satisfying the equation of motion, this term is 0, and this is my performance index. Okay, now I'm going to get del JA. Now I'll take this and get the derivative as we've done it in the past. But the only thing that's different now that I have integral instead of this was very nice, simple form. Okay, now we'll get this. So this will be 1/2. Then this will be del X transpose QX plus X transpose Q del X, and the same here, del U transpose R U, U transpose R del U. Okay, and then plus 2 del lambda transpose times AX du minus X dot plus 2 lambda transpose A del X B del U minus del X dot delta T. Now the X is n by 1. The X transpose will be 1 by n. So this is a scalar. This is a scalar. So I can write it like this, or I can transpose it. The transpose of this will be exactly the same as this, because it is a scalar. Now if I transpose this, it will look like this. If I transpose this, it will look like this. So now I can group these times 2. Group these times 2. Okay? Okay, so now I'm going to take this out and multiply times 2. Take this out and multiply times 2. Now I don't need the 2 anymore, because I have 2, 2, 2, 2, and then 1/2. So I'm going to take all these out. We have del X, we have del U, we have del lambda, and unfortunately here we have del X dot. So I have to change this from del X dot to del X. And how we do this, I'll just here say it on the side. The integral from 0 to infinity of lambda transpose del X dot dt, I can integrate it by part. So this will be the integral of this, which is del X, times the first. And then put the limits, and then minus the integral of whatever I integrate times the derivative of the first. Lambda dot transpose del X dt 0 to infinity. I'm going to plug this here. So now we have very obvious terms, which is this term and this term. They multiply del U. Okay? And we have this term multiply del X. And this term multiplies del X. And then I have lambda transpose times del X. Okay. So now this del JA, I'll group the terms now. 0 to infinity, X transpose Q. That's one of them. Lambda transpose A. That's the second. And then I have minus here. And minus here, it becomes a plus. So I have plus lambda dot transpose times del X. And the whole thing is del X. And then plus U transpose R plus lambda transpose B times del U. And then plus del lambda transpose AX minus x dot. Okay, and then this whole thing is dt. And what is left now is this term. This is the only term that's left. And this term now is outside the integral, and it is equal to lambda transpose at infinity del minus. Okay, and then plus lambda transpose at 0 del x at 0. Okay, now I want this to be optimum. So now this has to be equal to 0. It has to be equal to 0 for any variation that we have. For any variation that we have. So now, one more thing before we go any further. This term will drop out. Because at the final destination where I am free of any vibration, there's no change in the final destination. So this is go to 0. Okay, now from here...
Shouldn't the second term also be 0 because the variation of x at the initial conditions, which is always known, is 0?
Yeah, this depends on exactly, you know exactly the initial state, or you don't know the initial state exactly. If you know it exactly, then this will drop also. We don't need this anyway. Okay? Now we'll set the variations, because these are general, then del x, del u, and del lambda. Then we have three equations. One of them is very obvious. This one. The equation of motion has to be satisfied. Okay. The second one, this one. Okay. Let me rewrite this in the transpose form. In the transpose form. So this says R transpose times U. R transpose is the same as R because it's symmetric matrix. Times U will equal to minus B transpose times lambda. Okay? Or U will equal to minus R inverse B transpose lambda. Okay, now the last equation is the top equation. And top equation, I'm going to write it also in a transpose form. So now this will be lambda dot will equal to A transpose lambda. I'm sorry, minus QX. Minus Q and X. So now this says, or U is equal to minus R inverse B transpose and lambda. And then we have X dot is equal to A X. And instead of BU, I'm going to remove the B, I'm going to remove the U and put it in terms of what we have here. So this would be minus B R inverse B transpose lambda. The second equation, which is in the bottom, is lambda dot is equal to minus QX minus A transpose lambda. In matrix form, X dot lambda dot is equal to x and lambda. And then the matrix here that we have what is this matrix? Hamiltonian matrix. Now I can extract the Hamiltonian in this form. Now if I go back and then now combine these with one little trick, and we'll say here, let the lambda and x be related. Let them be related. Why? Because I want to write this, and instead of lambda, I want to write it in terms of x. In terms of x. So I'm going to make this little trick. Let lambda equal to a matrix P times x. Okay? And then now I have everything here. P transpose minus R inverse. Why I'm doing this? So I can take all this and group it in the gain matrix of the controller. Now, this is exactly what we've done. If we make these, and instead of vectors, we make a matrices. And we had here x dot, capital X dot, and we had here capital Y dot. These are matrices, not vectors. And we said now, I'm going to let P is a matrix that relates these two, and instead of vectors, matrices, which is, I'm going to have the P such that either lambda is equal to P x, or we make this capital Y which says that P is equal to capital Y x inverse. If we have this transformation along with the Hamiltonian matrix, we can extract the Riccati equation, we can solve the entire system. Now, this is very well understood for the LQR, and we showed it in two different ways. Now, the H infinity is just a piece of cake now. We write down the proper form of the J, follow the same procedure, and we get the corresponding Hamiltonian. Okay. After we finish this, then you have fantastic set of notes, because this you will not see in one place. Okay. Can do the same for the LQG, and I'll put it in the appendix, okay? And then now for the H infinity. And I'm going to start with the H infinity controller, because as we've done with the LQG, we showed that I have separation between the controller and the estimator, and each one of them results in a Riccati equation. So I'm going to start with the H infinity controller. Okay. I'll say here I want the H infinity norm of certain transfer function. This is equal to the maximum or the supremum for any frequency range. And this supremum is the transfer function, which is the output over a given input. Okay. Now, this output, I have to look at second norm. Second norm. So this is in effect, I am drawing the transfer function between the input and the output and looking at the peak value. Now this has to be less than gamma. Okay. Now we'll show you how to make this output. Okay. But this is the idea of the H infinity controller. Now I'm going to recast this in a different way. Or I can now make that this y second norm squared minus divided by this squared is less than this squared. Okay? And I'm going to take this and multiply it here and bring this here. So this will be minus gamma squared less than 0. So I want to drop this as low as possible. As low as possible. So I'm going to make this my performance index. Then let J is equal to this Y is just not, it's not just only the Y output that I'm measuring. Will show you that I can make this what I am measuring plus penalty on the control energy. Because if you look at this equation, it says now I want to minimize this J, which is, this is just not my X, which is the state of the vibration of the structure, but I can also include in this the control effort. I will show you a little trick to do this. And at the same time, I want to minimize this for the worst case disturbance acting on the system. So, because this, if this is the highest value, which is the maximum disturbance, I want to push this as low as possible. So now how would we do this? It's very easy. We know all the tricks. We know this. I can write it down by the H2 norm specification. This is nothing but the trace of the integral y transpose and y. And this is minus gamma squared w transpose w dt. So this is my J. So now we'll say consider the following system. X dot is equal to F and W, and then Y. I'm going to make this Y like this, Cx plus du. And I'm going to do this such that d times c is equal to 0. I think that's correct. D transpose and then d transpose d is equal to 1 or identity. This is a very nice trick, and the reason for this, I'll just say a little example here. if y is equal to, for example, it's equal to, let's say 1 and 0 times x plus 0 and 1 times u. So what this is saying now, that my y is nothing but x and u. Then y transpose y is okay. So with this little trick, whatever I want to use as my performance index has both the vibration and the control effort. The energy total that I want to minimize has the vibration and then has the control effort. This is very little trick. Now, this is what we want to minimize for a given disturbance on the structure. Now, let's look more on what we have here. This time this, these are two perpendicular vectors. So this is 0. If I multiply these two vectors, it is 0. Now if I take this vector and square it, it is 1. It is 1. So now this is very nice way of combining the vibration and the control energy in one form. Okay. Now I'll just take these, plug this here, and augment this with the fact that I have to satisfy the equation of motion of the system, take the variation, equate to 0 at the end, and then we extract all the equations and we'll extract the Riccati, the Hamiltonian equation matrix. I'm not going to do all this, I'll just write down and then we'll have it in the notes. So now, JA will equal to the trace integral y transpose is right here. Cx du transpose Cx du minus gamma squared W transpose and W. And then plus lambda transpose, and I'm going to make this also 2 here, multiplied times 2. Why 2 here and not here doesn't matter, because lambda transpose times AX du FW minus X dot, when this is satisfied, 0 times 100 is still 0. Okay? So now, and then I close this. dt. Now let's just expand the first term. The first term becomes x transpose, c transpose c, and x. Now I'll multiply these two terms together. Okay, so I have u transpose, d transpose times cx. D transpose times c drops out. Now, this times this, d, u transpose, d transpose times d, u, d transpose times d is identity, so this will be u transpose and u. This is what we've been doing in the LQR. This looks like my Q matrix. R, in this case, is unity. Okay? Now, then I have here minus gamma squared, and then the remaining part. And then now proceed as the LQR case. And then we'll say for any del U or del X, del U, del W, del lambda transpose, then we have the following. We have lambda dot will equal to minus C transpose C and X minus A transpose and lambda. And X dot will equal to let me leave this for a minute. I'll write down the original equations that we get from equating the coefficients of the deltas equal to 0. This is one of them. The second, U transpose will equal to minus lambda transpose B. The third, lambda transpose F will equal to gamma squared W transpose, and the equation of motion. I have 4 equations now. 1, 2, 3, and 4. Now I'm going to use 2 and 3 to eliminate U and W from this equation. So now the result is the W I eliminate it and replace it by lambda. The U I eliminate it and replace it by lambda. So this equation will be x dot ax, some terms times lambda. This is x and lambda. Then I can group them again in Hamiltonian matrix form. Then the final result. X dot, lambda dot. Okay, now for the LQR, that's what we have. These two are exactly these two. Now, because I formed my response Y in this form, then the C transpose C is equivalent to my Q. Now, if I don't have disturbance acting on the system, this term disappears. So I have B and B transpose. Now, making it in this form, subject to this constraint, made the R equal to 1 in here. Okay? The additional term comes from here, and it has the gamma in it. How can I solve this? Assume gamma. You have the Hamiltonian. Does the Hamiltonian eigenvalues lie on the imaginary axis? No. Then reduce gamma. Then reduce gamma. Then reduce gamma. Reduce gamma until they lie. Then we have a solution. The solution for this, I can extract from it what we have here. Okay. Now I want to calculate the control gain. How would I use this equation? In this equation, I can rewrite it like this. U is equal to minus B transpose lambda. Same trick that we did last controller, the LQR. I'm going to replace lambda by P and X. Why? So I can put this minus gain and X. This is exactly the same as the LQR. But the LQR had here R inverse. R, in this case, is identity. So B transpose P. But this P is P that solves this Hamiltonian matrix. This Hamiltonian matrix, not this Hamiltonian matrix. Okay? Just have a beautiful cup of tea. Think about this tonight. We'll see you on Wednesday. This sounds like a lot of math, but it is not. If you look in any control class and any control notes on Hamiltonian, on H infinity, he will give you this, and you sit down scratching your head. How did he come with this? Okay? All exactly the same. All of them exactly the same. LQR, this, and so on. Have a good evening. Where is he?
I'll give it to him.
Okay. This is the new homework. transpose C is equal to 0, and B transpose D is equal to identity or 1, depending on number of actuators. Okay, and we said that the reason for having this constraint is that we can have the vibration energy as well as the control energy in one representation. And we said now, you want to design or define and control gain. Okay. Such that U is equal to minus K and X. And we want to minimize certain minimize J. And this constraint X dot AX plus FW. So if we do it in this form, then we are saying that we have full state feedback. Or this is equivalent to separation principle between the controller and the state estimator. If we have a state estimator, then this would be X hat, and the design of the control gain will be exactly the same as if we had full state feedback, and we'll design the state estimator as if we have only the state estimator alone, so we can get the gain of the estimator alone because of the separation principle. Then we sit down here where J is the transfer function, G, and it is the infinite norm, and this G is the transfer function between the output Y and the input W. And then we said that if we write it in this form, and this is equivalent to the Y 2 squared W 2 squared, and this norm has to be less than certain gamma, where gamma is a positive number. And then we did the trick on this J, so we can transform it in a form that we can track it with what we have. Then this will yield Y second norm. I'm sorry, these are if we square them, then this becomes minus gamma squared W squared is then 0. And now we, from the definition of the H2 norm, then we can replace these by the trace of the integrals of y transpose y minus gamma squared w transpose w, and then this will be all dt, and this will be my performance index that I like to minimize. And this is our G. Now if we want to minimize this and at the same time satisfy this constraint, then one way of doing it is using Lagrange multiplier to minimize J subject to the constraint, which is the satisfying the dynamic equation of motion of the system. Then we'll use the Lagrange multiplier approach. Now we have this objective function is function subject to the constraint. Now I'll augment these and form a new objective function, and I can solve it as an unconstrained optimization. So this problem now is a constrained optimization. Constraint optimization, we don't know the solution of it because it's a simple fact. For example, if you look at here, this is a function, and then I have a single variable x. This function might look something like this. So if this function is unconstrained, or the design space is unconstrained, I know where the minimum is, which is here. So this x is the unconstrained optimum. But now if I take the same thing and then instead of leaving this design space unconstrained, I'll impose, for example, a constraint here. And I say I want to find the minimum of this function subject to this constraint. So for example, I can say anything for x greater than this value, x0, is not acceptable solution. Okay? So this can be, for example, the dynamic equation of motion. So now the minimum here is right here. And this is completely different than what I can get by partial differentiation of f with respect to x. And in this case, the minimum does not occur at partial is equal to 0. Okay, so now this is unconstrained optimization, this is constrained optimization. But now what we will do, we'll augment the constrained objective function with the constraint. Then I have unconstrained space. There are many ways of doing it. This is one way. Another way is, for example, the penalty function method, and so on. So penalty function, instead of just looking at the constraint alone, I look at the constraint square. How far I vary the constraint on the positive or the negative side. Okay. So now accordingly here, we'll transform the constraint optimization problem to unconstrained optimization by augmenting J by the extent of violating the constraint. So now accordingly J will become like this. So like once we do this becomes unconstrained optimization, then I can apply this simple equation. So I can find the best control gain that will satisfy this fact that partial the objective function with respect to the variables is equal to 0. By the extent of violating the constraint, then optimum is reached when del J augmented is equal to 0. J augmented will be equal to, again, the trace of the integral from 0 to any time. For our, in all this course, I'm using this as infinite time. But there are some problems that you like to have specific time, and this requires another term here. So if you want to meet an object at certain instant of time, you have to have the integral bounded between 0 and t infinity. So if you want to rendezvous with a spaceship at certain instant of time, you have to terminate your optimization at this instant of time. So we have y transpose, y minus w, and then I augment this now by lambda transpose. And then how much we violate the constraint. So the constraint looks like this: ax plus bu plus fw minus x dot. Now, this is dt. Now, to make this nice and when we get the result in a compatible form, I'll just scale this by multiplying it times 2. Okay, we don't have to, but I can define a new Lagrange multiplier. Lambda bar is equal to 2 lambda. Okay, so anyway, so I can get nice clean result, I'll do this. Now this is my constrained objective function. I want to minimize this, but at the same time I want to minimize how much I deviate from the constraint. So this is now the deviation. If I'm deviating from this is equal to 0, then I am adding this to this, jacking it up, and I still want to minimize it, so I can keep pushing it down. This reduces, and at the same time, if I satisfy the constraint, then this term will drop out from the picture. So now this, an unconstrained optimization. So this is an unconstrained optimization. And has optimum when del J augmented is equal to 0. Now we have J augmented will equal to the trace integral, and then I'll replace y from here. So I have X plus D U transpose, CX plus D U minus gamma squared, and then plus the remaining term. Which is this Lagrange multiplier, 2 lambda transpose the first term. When I expand the first term, then this will be X transpose, C transpose C, and X. And then the last term, U transpose, D transpose D, and U. And then I have cross terms, cross multiplication term, the U times the X, and the U times the X. So for example, if we take the first term, then we have U transpose, D transpose C, and then X. And the second term is the same, which is, I multiply this times this, now I multiply these two, so I have X transpose, C, and D, and U. Okay, now from this assumption that we have here, D transpose times C is equal to 0, so this term will drop. And again, the same, if I take the transpose of this equation, then it becomes C transpose D, it is also 0, so this term will drop. The main reason for this assumption, the main reason for this yellow assumption is we get both the vibration energy and the control energy. Each one is separate. If we don't, and we leave this, we know the solution from the homework problem that we did 2 weeks ago. So this is equivalent to the term N that we had, okay? But this is now a very clean way of separating the vibration energy and the control energy, okay? And then the remaining terms are and then now we'll do the variation on the final result, and then put it all in del X, del U, del W, del lambda transpose. And then perform the variation of JA and put it in terms of del X, del U, del W, and del lambda transpose. And the result was like this. U is equal to minus B transpose lambda and H dot lambda dot X and lambda gamma squared. And now this is my Hamiltonian matrix H. And I can put this Hamiltonian in the associated Riccati equation. So we should say algebraic Riccati equation. This is A transpose P, PA. And we have minus B, B transpose minus F transpose over gamma squared. And then we have here E and B. Now I'm going to make the following, and we'll see here let lambda is equal to P times X. And when we do this, and I combine these two equations, then we have U equal to minus P transpose P and X. And this will yield this control game K. The solution here, P has to be symmetric, positive definite. Okay, so now we how to extract the K. So we'll here assume a gamma. When I assume gamma, input gamma, and then compute H, and then I'll go and compute eigenvalues of H. And then see that the eigenvalues don't have any of the real parts lying on the imaginary axis. Of the eigenvalues is equal to 0. Say is the absolute real part of the eigenvalue greater than some epsilon. If it is yes, then we go and reduce a gamma, and then we go back again here. And if it is no, then we stop. once we stop, then we have here the minimum value of gamma. Now I take gamma and I put it in this algebraic Riccati equation. We have this number, we have the all these matrices. The only thing that's unknown is P, solve for P. Then now, we have the algebraic Riccati equation. It has A transpose P plus P and A minus P, and then I'm going to put here, for example, Q and P, and this is equal to minus C transpose and C. And this Q is equal to B transpose minus F transpose over gamma squared. This is my algebraic Riccati equation. Solve for P, and P will equal to A, Q, and C transpose C. I'm sorry. ARE, which is the algebraic Riccati equation solution from MATLAB. And we get the P. We have to be sure that the determinant of P is a positive number. Has to be a positive number. This has to be positive. We have the P, then we go now and calculate the gain K. The handout that you have is for the example that we've been doing for the last section. I'll begin first by looking at the value of gamma, the optimum value of gamma. So this is, the whole thing is this part. And I want to get the minimum value of gamma. So all this section is summarized in these two lines. I begin with an initial guess, and then apply the constraint optimization on this function routine, starting from this initial guess. This function routine, you have the handout that showed how to calculate for this system the H infinity for it. Okay. Now I have the mass matrix, the stiffness matrix, and this is the rod with two elements. And then I get the A matrix, the B matrix, and then now I form these two matrices. Why? I have to form these so I can satisfy this and extract here an output which has two things. The output has the first few terms are what I'm going to measure. The last few terms are the control effort U. The control effort U. So now I have here element 1, element 2, and then we have nodes. I will call this node 0, this is 1 and 2. So now my system vibrates on longitudinal vibration. So I have here U1, I have here U2. If I put this in the state space, I have also U1 dot and U2 dot. My state vector X will equal to U1, U2, U1 dot, U2 dot, and the whole thing is transposed. Okay. I'm going to measure only U1, for example. Okay. Then if we measure only U1, we are used to writing the output is equal to 1, 0, 0, 0 times X. Okay. When I do this, then the output, let me make this output Y bar. Then the output that I'm getting from here is just U1. This is horrible, huh? But U is deflection, not control effort. Okay? U is deflection. Let's make this. U is the deflection. Longitudinal deflection. Okay? Now I don't want this only. I don't want this only. I want also how much control effort I put as an output. As an output. So I'm not gonna make my Y like this. I'm gonna make this is Y1, and I wanna get also Y2 bar, which is equal to my control effort. I want to get this as U. Okay, so now I'm going to form this in a matrix form. This is what I want as my output. So my new output is equal to this vector, Y1 bar, Y2 bar. Okay, and I'm going to put it in this form. C and the X is the same. U1, U2, U3, and U4. Plus a D times U. Okay? The result that I should get from here is U1 and U. U1 and U. So now, how would I do this? I'm going to make this C like this. 1, 0, 0, 0. Because when I multiply this times this, I'll get U1. I don't want anything from here. So this should be zero. Now I want the output from the second row only u. So this should be 1 and this should be. So before you do the H infinity controller, you have to come up with this combination. Okay? Why is this combination? Now, if I take this and multiply it times the transpose, I satisfy this. If I take the last vector 0, 1 and transpose it and multiply it by itself, I satisfy this. So now I have everything is broken down, so I can get the vibration energy as well as the control energy. So you have to come up with these two matrices. These are not the C and the D that we are used to. We are used to in the LQR, this is what I call my measurement matrix, because I have all the states and I only measure one of them. In the H infinity, I have to have access what I measure as a state and also my control effort. Okay, so now from here, this is my C and this is my D, and both of them satisfy these constraints. Now we go and form the Hamiltonian matrix, and the Hamiltonian matrix, I want to get its solution using the algebraic Riccati equation. So we form this Riccati equation, and this Q, I put it here as B, B. This is my Q. So it has B, B transpose minus F, F transpose over gamma squared. So B, B transpose, and then this is F and F transpose. So I have the controller here, and I have the disturbance here. You can try also other places. You know, like for example, I can have the controller here, and I can have the disturbance here. So depending on your system, if you want to measure the tip displacement, then this would be 0, 1, and so on. But this will illustrate what we have in mind. Anyway, I just took the B and the F are the same. The B and the F are the same. So now we form the Hamiltonian. And then I form this Q matrix. And then now the C transpose C here. Now I go and solve the algebraic Riccati equation. A, and then the BB, and then the CC. The result is P, and then the gain is right here. When you do this, and you can come and say the determinant of P. You will see that this determinant is positive number. Then everything is fine. Then we have the right solution. Now, then the gain. Will be 0.047, 0.1016, 2.257, 1.617, 2. Okay, now we're done from this case. Now I want to compare what we have with an LQR. Okay. The LQR case, I don't have this term. And I have this Q corresponding to R is equal to 1. corresponding to R is equal to 1. And then on this side, I have minus C transpose C. C transpose C, we have the C here. Then I have to multiply C transpose C, so I can get exactly the same right-hand side for the algebraic Riccati equation for the LQR. So for the LQR, R has to be 1, and my Q has to be C transpose C. So we have the C is matrix was 2 rows and 4 columns. When they get the transpose, it becomes a 4 by 2. And multiply 4 by 2 by 2 by 4, the result will be 4 by 4 matrix. So the Q of the LQR looks like this. And if you look at what we have, it has only said the important state that I want to control is U1. I don't care about this, or this, or this. So we can compare apples and apples. Okay? So I have the Q is the same as the H infinity. The R is 1 because the fact that R inverse is 1. Now I can go in and calculate the gain of the LQR. So I have now the gains for the 2 cases. Now I'm going to go and do 2 things. We have the system description, we have the gains. I can put them on Simulink and do time domain analysis, or I can also look at frequency response analysis. Okay? Frequency response, I have the closed loop system matrix, and then I have the C and the D and the B for the H infinity. Then I go and apply the state space to transfer function, and then plot. Because I took here the A closed loop, then I can do directly the both diagram, or I can get the open loop and then use the command closed loop to determine the magnitude and the phase. The same for the LQR, and then I'll plot the result. Okay. I'll show you this first, the frequency response. So right away from what you see here, you see why H infinity, or what the H infinity does. Okay? H infinity squeezed the peaks, pushed them down. That's where we are. The LQR has higher peaks, much higher peaks. The corresponding gain for the LQR, this is the gain for H infinity case. This will be 0.0. So the effectiveness of H infinity appears very clearly in the frequency domain, because it's a frequency domain function and try to squeeze the peaks and bring them down. And we can look also at the time domain. And you will see what H infinity does in the time domain. It puts the brakes on the system. Puts the brakes on the system. It doesn't make it go at high amplitude. When it tries to overshoot and go lower, so you have very large peak, puts the brakes on it. Bring it back. Bring it back. So here you have the travel is from 1 to minus 0.3. The travel here is from 1 to almost 0. So it puts the brake on the peak amplitude. It doesn't make it overshoot. But the result is on the other side. Okay. Instead of going this way, it goes the other way. But eventually comes down. So the power of h infinity squeezing the peak amplitude both in the time and the frequency domain. I'll stop here because I'm dead today. I will see you next time. We owe you an exam, so we'll do it sometime. Okay, it'll be not next week, but the week after. Thanksgiving. Okay, after Thanksgiving. B1 transpose is equal to 0. And the solution for the control action was U is equal to minus B2 transpose P C times X. Okay, I solved this in detail. Now, for the remaining part, which is the estimator, I'll have the same pieces of information that D21 transpose D21 is equal to I, and the B's and D21 transpose B1 equal to 0. And then now we'll have by the duality H observer will equal to instead of the A, I'll put A transpose. So this will be A and A. And instead of the C's, I'll put the B's and the transpose. And the top line will be C2 transpose C2 plus C1 transpose C1 over gamma squared. And then the Riccati will be A P observer A transpose B1 transpose minus P observer C2 transpose C2 minus C1 transpose over gamma squared equal to 0. Exactly the same we can come up with the controller of the observer gain, and the observer gain L observer will be very similar to what we have here, but it will be P0, and then instead of the B will be C transpose. So to make these look the same, I'll just here say K control. So now we have all the theory that we need for H infinity. Now we have to design it in a very simple way. Again here, this is the useful formulation. You will see in some of the books, these terms are not zeros. They put these terms, but this is just waste of time. Because all the design, as we've shown, this is what we need to get the control performance index, and this is what we need to get the observer or the estimator performance index. Now we have these two main building blocks. Then we come here. And I'll have, this is my structure. And the structure has disturbance acting on it. And then the equations that I put here, I had two types of outputs. One output that I like to control, one output that I am measuring. So what I am measuring is y. So now we have the two main components of the H infinity controller. I take the y, put it in the H infinity filter, which is Kalman filter, with the gain this much. I need for this Kalman filter I need to put U. This much. I need for this Kalman filter I need to put U. Now I have these two, then I get from here X hat. I get X hat, I go in, H infinity controller. This block, we have all the details from the LQG. So I have the Y and the U. From these I combine with the L0, get the estimate of the states. Only measuring small subset generate the entire state vector. The entire state vector is known, times minus Kc will give me U. I'll take this U and give it back to here. And then between these two, I'll connect to this. We can do all this one step at a time as we've done it in the LQG. Now I'm going to take this block. This is still my structure. And this is now my entire controller. Let me just make this green line here, huh? Okay, now this little box that I have here, this box. I input to this box Y, and I get out of this box U. So this red box is right here. Now if you think of this little box as an output controller, I give only to this box the output that I'm measuring, and I generate from it the control action. How it is done, the details are right here. Okay? And this box has this output controller gain K. This is capital K. Output controller. This capital K includes everything inside this box. Okay? Now I'm going to call this structure capital P. And this problem is called 2 I have 2 here, and I have 2 here. Input and output. The box of the structure has 2 inputs and 2 outputs, or 2 port and 2 port. Okay, and that's what we will do this lecture. Next lecture we'll do 4. I'll add to this box another box here to include the uncertainty of the system parameters. So I'll put it on the top here. Okay. Now, any structure, I can reduce it to this general form. And this is the general, well, we'll say half general, H infinity form. So for example, again in a D. I can recast this in this form. Why? Because this is how MATLAB is structured. Any system assembly or connections, I can reduce them to this form. Once I have this form, I put it in, and I have one single command. I generate everything. I generate how this will look like. I generate how the transfer function look like, how the co-sensitivity function look like, and sensitivity, and so on. Once we put the uncertainty, then we can check system stabilities and so on. Okay. So how we do this? Allah define this vector. This vector is all the exogenous inputs that I put in the system. One of them is R, one of them is D, and one of them is M. Okay, so to follow the same I'm going to make this D, R, and M, or W1, W2, and W3. Okay. The Z, I'm going to select it in this case, the error. The error, I want to kill the vibration. So if this is 0, then I want to kill this parameter Z, which is the vibration that I'm measuring. And then I'm going to call this, because I have Y here, I'm going to call this term V. And this term is what I send to the controller to generate my control action U. So this is my control action here. So what I send to this controller is what I have at this location, which is R minus this, which is, oops, which is y plus m, the output measurement plus the noise. So that's what we have here. So here will be minus y minus m. And then the last thing is we have u is equal to k times v. Now I have the two ports have W and U. The other two ports have Z and Y, or Z and V. So now I have W1, W2, W3, and U. And then I want to relate this to Z and V. I'm sorry, reverse. The output is Z and V, and the input is W1, W2, W3, and U. Or these, based on what we have here, this would be D, R, and N. When I come up with this matrix, then this would be the transfer function of the structure. Okay, and now Z is equal to Y minus R. Y is what we get here, which is G times U plus D. And then minus R. And then plus 0 times M. So now we replaced the Y from the block diagram. So now I can take this and put it here. Now I have D, which is 1 or identity. And then I have R minus identity. I have 0. And then I have G. Now the second term is V. V we found it to be equal to R minus Y minus M. So I have R, and then the N is minus N, and then the minus Y is minus G and U, and then plus D, or minus D. This is GU, so this would be D plus GU is equal to Y. Now I can take this and put it here. Minus D, R, N, minus G. Now we have everything, we have the P, then I can take P to MATLAB, and put how many inputs I have, how many outputs I have, find controller K, and we're done. Okay, so this is one simple example that cast it in this form. to redraw this with, instead of like what we have here, I'm going to add the weighting matrices to what we have. So we can redo this diagram again. And this, we've done it by hand. Like looking at what we have from the block diagram and do this. And then I'll give you a very small program that you do it with MATLAB, so you can generate everything by looking at how these, just the inputs and outputs, and then it does all the calculations for you and generates the P matrix. Okay. So now I'll erase this. This is an example only because I'm using Z as one single output. Okay? But I can have output U, and I can have output here any place I want. As we did in the general formulation for the controller, I had this and this at the same time. And that's what I'm going to do now with the weighting, say example 2. Example here, MV. I can put noise also, but I will not put noise here. So now here is system with weighting matrices or transfer functions. Now I want to put it in this form. So I have here W is the disturbance that we have, and then we have U, and then the output is Z. I have 3 Z's, and then I have this Y. So now we can redo it like this: Z1, Z2, Z3, and V. This would be my V, and this is equal to the W, or the disturbance, D, and U. Okay, and then again from the block here manipulation, Z1 is U times WU, so it is 0 times WU1 identity. And then Z2, the same story, WT times G, and then here is WS and G, minus I minus G. I'm going to break this into 2 pieces like this. This is the inputs. And this is the outputs. And the relation is related by system P matrix, P. I'm going to break this like this. I'll partition the P matrix like this. Then we have the Z and the V. This is D and U, or W and U. Now I can expand from here. So we'll have Z is equal to, and V is equal to times U. Okay. Now I will rewrite the bottom equation. V is equal to P21 times D plus and P22, and then I'll replace the U from here, which is equal to the V times the K. And this now will give me, I'll put V's on one side and D on one side. So I have I minus P22 K and V is equal to P21 and D. Or V is equal to I minus P22 K inverse P21 and D. Come to the top equation and replace U again by KV and replace V from here. Okay, we don't need this. Then Z will be equal to P11, P12. Okay, and V, I'll replace it from here. I minus inverse P21 and D. Now I'll factor out the D out between here and here. So if you look at the term between the yellow brackets, it is in effect, I took the structure and cut it into two pieces. Piece relate to the controller, piece relate to what I am interested in. How much disturbance, how much is the control output. So now the controlled output is Z, the disturbance is D, and the transfer function between them is this transfer function. This transfer function is called F, L, P and K, and this is Z, and this is the disturbance D. And I don't need all this. And where the FL P and K is called linear fractional transformation, and the little l stands for lower. Why? Because I'm looking at the lower part of P. I have another part on top because of the uncertainty has similar transformation called FU, has the uncertainty of the structure. Now the purpose of the controller is, and the controller here is everything. The estimator plus the H infinity controller. The controller job is minimize the infinite norm of this fractional transformation matrix, and the controller job is to, our job is to find cap K, the augmentation of the estimator and the controller. Find K to minimize this. Now, all this has these matrices, W, WT, and WS. I'm going to just take these and plug them in this equation so you can see the final result. Okay, so I don't need all this. And we said that this term is all called then the FL P and K. P11 is right here. Zero, zero, and WS and I. P12, which is this matrix. W, WT, and WS and G. And then I multiply this times K. P22 is right here. Minus G. So this would be plus GK. And this whole thing is inverse. P21 is minus identity. Okay, I don't need to write the identity. Now let's clean this. And I'm going to write this W, U, K. If you remember from the past, we said that I plus GK inverse is sensitivity matrix. And then here, WT, GK divided by this. So this is the co-sensitivity matrix. And then WS, GK, and this is T. Now I want to clean this more. So this would be minus here, WU, ks minus wt and t. Now here, have ws, factor out I minus t. I minus t is equal to s, because I is equal to t plus s. So now this will be ws and s. The bottom line of all this, I want to now get the infinite norm is nothing but the infinite norm of W U times S, WT, I'm sorry, WT times T, WS times S. Now we can play all sorts of things. You know, like if I don't want to put weight on this, this is out. Now, if I have these two, I have two conflicting things. I want to minimize this so I can get benefit for the disturbance reduction. But I'll pump this up because the sum is constant. Now we have a very nice optimization problem. I will not continue this lecture, okay? We'll do it next lecture. Today we just want to make an example before I put these weights. So we see how to put these weighting transfer functions and the formulation. Okay. This might look too abstract, but the final result, as you will see, it is one line, and you will understand what this line in MATLAB means. After we put this one line, then you say, wow, all this math is boiled to one line. So you know exactly what's inside this line. I'll do an example. All this. I'm going to take a system and make it very simple structure, and make it very simple structure by eliminating a lot of dynamics. So for example, I will take a system and I make it like this. x1 dot, x2 dot, and then I'm going to measure x2 and m. X1 dot is equal to u, and x2 dot is equal to x1. Then if I combine these two, then x2 double dot is equal in effect to u. Okay? If I take this and differentiate it, then this x2 double dot will equal to u. And this will say now that x2 is equal to 1 over s squared times u. So this is very simple mass, inertia, and I neglected the spring, and neglected the dampers, neglected everything else. Okay, so I made it very crude system. Okay, so this is in effect what we have is a double integrator system. So now I can make it here. This is my system. And the output from here is x2. And I'm going to put here some noise and the measurement. And the input is disturbance plus the control action. So I have here disturbance. And I have control action. And I have K. The noise plus the output is my Y. This is x2. And U. Now I want to reduce this to the standard form. So the standard form has D and N, or we'll make it as they are, N and D. And then I have the outputs, x2 and u. And K, Y, and u. And then this is my plant P. And we need all this. So what we need is to write down here is the output, x2 and u, and then the inputs, here the N, D, and U, and we find this matrix P. program which is ended up by this last statement. This is called the system interconnect. This is command to interconnect the system. We will define what is the transfer function of the simple system, which is this system with this. This is the transfer function of the basic system without any disturbances or noise or anything on it. Okay? And then this system has this output. So the basic system is x1 dot is equal to 0x1, 0x2 plus 1 times u. And then x2 dot is equal to 1 times x1 plus 0x2, 0 times u. Or this now will be like this. x1 and x2 and the last equation we have y is equal to 0, 1, x1 and x2 plus 0 u. So now this is my basic system. Everything here is known now. So now I can go I have the A matrix. I think I call it like this: A, 0, 0, 1, 0. B matrix is 1, 0, transpose. The C matrix is 0, 1. And then the D is 0. There is no D. Now I can get the transfer function of the system. Transfer function of the system will be the pack of the A, B, C, and 0. So now,
3 by 3.
Hmm?
So G is 3 by 3.
G,
Yeah.
yeah, whatever it
There's
is.
nothing else. I mean,
Yeah.
it's separate.
Yeah, so this is the G that I have here. This program is all symbolic, all symbolic. Now, this is a subroutine, small subroutine. And this subroutine, I called this subroutine P, or generate P. This is generate P subroutine. So now I'm going to make this in a separate file, and I'm going to call this M file generate P. I'm going to call this file. The result from this is P, known. Now P will be known. I'll put what is the input variables, what are the output variables, what are the inputs to G. What is the inputs to G? Input to G is U plus D. Input to G is U plus D. So this is the input to G. The input variables, D, N, and U. N, D, and U. These are, everything is coming in. Everything is coming out. X, U and Y. X2, U and Y. Okay. The output of the G is G. The output of G is G. And then the U here is U. And then the output of G plus the noise is Y. Output of G plus the noise is Y. Now, the system output name is P. I have this P now. Then I go in the second page. Sorry, you have everything. Yeah, in the second page that you have. These are what I have on the right-hand side. The A, B, C, and the G pack. I call generate P. That's what you will get. What you will get, forget the last line, last row, and the last column. These are not included in the P description. But this is MATLAB description of the P. Now, how we generate this? You know, I can recast this from here, exactly. From here. Okay? How? I'll define a vector, D and N, as the disturbance. And I put it here. Then I have my U, and then generate everything. I'll do it in a couple minutes. So this is my P. Now I go in, and then ask for this command. Synthesis of the H infinity controller. Synthesize the H infinity controller for me. I have the P. Everything is augmented in it. Now this example that I have has no weighting matrices. Okay? I can put the weighting matrices and generate the P corresponding to the weighting matrices in a very simple form, because I will just say this is nothing but this times W. This is nothing but this times W, okay? And then assemble the P for me. And then now I'm going to call on the left-hand side 3 parameters that I'm interested in. The controller gain of the entire assembly. This has the estimator and has the H infinity controller, both of them. This is the total K. And get me the co-sensitivity transfer function. So this is GK divided or multiplied times I plus GK inverse. And get me the gamma, if you're interested in gamma. You know, we're not interested in gamma because this is all transparent for me. What is happening is you minimize gamma for the controller, minimize gamma for the observer. And then the result is just multiply everything and get me this. I'm not interested, but you'll have it anyway if you want to see, and I'm printing it so you can see the propagation of the minimization process. Now I put P. Write please these numbers now. These numbers. First number, the number of controllers. Second number, the number of measurements. Number of controller, number of measurements. The third number, the smallest value of gamma. And the largest number is the maximum number of gamma. If these are okay, these are my guesses. If these are okay, you will find the solution. If it's not okay, the program will tell you there is no solution in this. Increase the range. Because maybe gamma minimum is more than 100. Okay? And then the last number is the tolerance. How much I want to have until I stop my optimization of gamma. So that's all what we have. Now it goes in and does these iterations. See, we start the gamma at the highest value, 100, and then it iterates. You know, like you could see here, this is 2.62 and then 2.607. The difference is 0.013, which is greater than this tolerance. So it will do one more optimization, and then the difference now between these two is 0.006, so it stops. So it's within the acceptable tolerance. Now this is the value of gamma minimum. Here it prints the values of the norms, the minimum value, eigenvalues, and so on. And these are for the controller, the X's for the controller, these for the observer. Now, the k and t that we will get are unfortunately in this packed form. They come in this packed form. Now I have to unpack them. I have to unpack them. I have these, I pack them in a transfer function. If I have the transfer function, I unpack it to get these. So now I go from k, which is for the controller, and the t, which is the consensitivity, and I go and unpack them. Unpack the t. Once I unpack them, I have the A, B, C, and D. Then I use the state space to transfer function to get the numerator and the denominator. I have these, numerator and the denominator. Okay. I have the noise and the disturbance. I can look at either one of these two effects. And this is the denominator. Now for the controller, I'll do the same. And then realize the controller as numerator and the denominator. Now I'm going to write how this will look on the body diagram. So I select a frequency range. And the frequency range is from minus 1 to 2, and I divide it into 200 steps. Minus 1 means frequency, 0.1 radians, until 100. And I divide it into 200 steps. I'm going to plot only the cosensitivity. Cosensitivity. Numerator, denominator, and W, which is the frequency. Now I have two inputs, N and D. Okay? And then I'm going to plot the result. The result is right here. They're very close to the 1, the maximum value. And they're going below the 1. Do I like this curve? Fine, I'm done. If I don't like it, I want to shift this down or up. How would we do this? With the W's. I selected the W's so I can move this characteristic curve up and down. When I move this up and down, K, the controller will move with me. So I can shape the controller to reject disturbance as I like it to be. Is this clear? Okay. Now, so the whole thing comes from this just single statement of the H infinity censuses. And please look at the help file so you can look at all the alternatives that you can get along with this. But that's all what we need, and I just did the most simple because that's what will show you that we are minimizing gamma until we come to the tolerance that we want, then we stop, and then we have what you need is the control gain and the T. Now if you look at the controller, I unpack it, and then put it in numerator and denominator, so it looks like this. Now if you look at the controller here, I have the numerator is multiplied times 10 to the 5. The denominator is multiplied times 10 to the 5. So these two will cancel out. And then this is S 5.87. I'm going to take the minus here and put it here. Minus times S plus 2.3. And the denominator is 2.29 S plus 5.2 2. So the controller is first order in the numerator, first order in the denominator. So it is first order here and first order. It's a very simple controller that you can implement very directly. So you can put this block inside here, whatever measurement that you get, you multiply by this, feed it negatively back to the plant, and then get the response. Okay, I think that's enough for today. We'll do the weighting next time, and then you have fantastic H infinity chapter. So we're done from all this.